Okay, welcome to lesson 10, and what we're going to do here is extend the idea of energy to a concept called heat. And heat is the change in energy at constant pressure between two substances that are in contact or between the system and surroundings. And what I want you to do right now is to pause the video and record this definition in your notebook. Okay. Glad to have you back. And now what I'm going to do is take you through an example. And again, even though this is an extension on what we've already learned, there's nothing that is different here than the principles that we've already gone through. So the best way to learn about this is to just go back through an example we did a couple of videos ago. So we're going to have a chunk of zinc metal. All right, and we're going to heat it up using something really hot like a candle, which I'm drawing here. All right, and then next door to that, we're going to create a situation where again we're going to have our system and surroundings, and to be consistent with everything that we've done, the system is going to be the zinc. So I'll go ahead and name that right now. It's the zinc is the system. All right, and we're going to take the system and we're going to take and put it inside the surroundings. So I'll draw a big box here. This is going to be our system, and it will have the zinc metal in it. All right, so let me get this here. So here's the zinc. This is the system, and the surroundings will be the liquid that is around it, and the liquid that we're using is H2O. All right, now we've heated the zinc up using a flame, and so you know that it's bleeding hot when we put it in here. So I'm going to label this compartment as hot, and the liquid that is surrounding it is cool. So going back to the first few videos that we have the classic situation here where we have a hot object that's been put in contact with a cool object, and you should recognize at this point that kinetic energy is going to move from the hot object into the cool object. So at the beginning of the process, before we've moved the zinc in here, our surroundings are going to have a certain temperature. We'll assume that it's at room temperature. So the liquid's going to be like 25 degrees centigrade. That's typical room temperature. And the zinc metal is going to come in at a temperature that's going to be, highly elevated. I don't know what it's going to be. You're heating this thing in a flame, so it's going to be hot enough to, burn the bejeebies out of you. And then we're going to move it, and we're going to put it down into this liquid. It should be common sense to you that the zinc metal is going to cool down. The liquid surrounding the zinc metal is going to warm up. And eventually these two objects, because they're in contact, are going to equalize in temperature and in energy. Now, what's different about this is just that we're going to extend the idea of energy. We're going to redefine it into a more sophisticated type of energy. So if you look back at the definition now, we're going to define heat as a change in energy. All right, it's a change in energy. Heat itself is not like a thing, right? It's a change in energy between two substances which are in contact that have a difference in thermal energy to start with, which we have here, right? Because the zinc's been heated in a candle, and the liquid has been sitting at room temperature, and then we put the two together, right? And there's going to be a change in energy of the entire thing. Remember that the system and the surroundings together compose another overall system that we're going to call the universe. So I'm going to define my universe as being the system plus the surroundings. So that's when I say that we're going to be more sophisticated. Now, this is one of the things. So we're going to combine the system and the surroundings together, and we're going to call this the universe. So in the end, after the energy is transferred from the zinc, the thermal energy from the zinc into the liquid, eventually the system and the surroundings together are going to unify. They're going to have the same level of energy between the two, and the temperatures of the two will have been adjusted. All right, so now let's talk about how this energy is going to change. So when we move the zinc into the liquid, it's at a much higher temperature. We can show it this way. So the temperature of the zinc, all right, and this is before moving to the liquid. Before moving to the liquid is going to be at a much higher temperature than the, let me define this as LIQ. So this is going to be at a much higher temperature than T liquid. Now what does that mean? It means that the zinc pellet is going to have a much higher kinetic energy and than the surrounding liquid, and so we're going to have an energy difference, and energy is going to flow towards the region that is lower than energy. So we can show that this way, and I'm now going to redefine this. So it's going to be, I'm going to call this negative H for the new way that we're defining the energy. So this is thermal energy, and it's moving into the liquid, which is going to be plus H. So what's going to happen out here in the surroundings is that the T of the surroundings is going to rise. So T surroundings rises. It has to go up, right? Because you've taken this hot piece of zinc, you put it in there, energy is transferred. If it makes you more comfortable, remember that the zinc metal itself is going to be at a higher kinetic energy. So kinetic energy will move from the zinc metal into the surroundings. All of this is perfectly consistent with what we're talking about right now. We're just calling it something different. I've changed the name of this to H, right? So the temperature of the surroundings is going to go up. Energy is moving into the surroundings. At the end of this, the energy of the surroundings is going to equal the energy of the system. Okay, that's what's going to happen at the very end. Now, we're going to define this change in energy, and this comes down to the fundamental of what delta H is. All right, so this is a change in energy after the process is over. So we have gone from inputting the hot zinc here, the energy change happens, the whole universe now settles out at a new temperature and a new energy, which is the same for both of the objects. So the change in H, which is going to be the delta H, is going to equal where the energy started from. This is for the system. So where the energy finishes minus the energy of where we started. So this is final energy of system. That's the zinc, right? Let me put that in here. So this is the zinc. And the H1 is the initial energy, where we started. Initial energy of the zinc. And the change in energy here is going to be equal to a negative value overall, because the zinc metal had to lose. It had to lose energy, right? Because when we put it in there, we put it into the liquid, it was at a higher energy than the surrounding liquid. So energy had to be transferred from the zinc. Now, to tie all of this back to what we've been doing, what we want to do now is define what's happened relative to the zinc and relative to the liquid from the point of view of exo and endo. So notice here that the change in energy for the zinc is negative. So for the zinc, this process was exothermic. And for the liquid, the process is endothermic. All right, and that should make sense to you because the temperature in the liquid had to rise, and the temperature in the zinc had to go down. It had to go down in the zinc because energy was given up by the zinc into the surroundings. All right, and to finish this off, what you need to recognize is that we also met the law of conservation of energy here. So the delta H for our system, the change in energy for the system, equals the change in energy of the surroundings. So whatever we lost in the system was directly gained in the surroundings. All right, and with that, this concludes the video, and we'll see you on the other side.